This medical fMRI scan illustrates the seductive promise that has driven educational research for the last decade. By mapping how learning physically occurs inside the brain, researchers believed we could bypass centuries of pedagogical guesswork. The expectation was straightforward. If we could pinpoint the exact neural mechanisms governing core functions like attention and working memory, we could automatically extract universal scientific truths and apply them directly to how we teach. But a biological view of cognition is strictly isolated and tightly controlled. Actual learning environments are dense, chaotic, and saturated with overlapping stimuli. We currently know more about the brain's physical architecture than at any point in human history, yet that biological mapping has not yielded proportionate improvements in educational outcomes. Attempting to take findings from a neuroimaging lab and port them straight into a physical or virtual classroom has consistently failed in practice. The pipeline from neural anatomy to teaching strategy is broken. To understand how people actually learn, we have to completely reevaluate how we apply brain science. The traditional approach relies on a structural flaw. Researchers and educators attempt to take a single brain imaging study and convert its findings into a rigid instructional design principle. This ignores the severe environmental mismatch between these two disciplines. In a laboratory, scientists directly manipulate isolated physiological variables to determine exact cause and effect. A student's daily life is dominated by noisy, uncontrolled, contextual variables that entirely corrupt those clean laboratory dynamics. This is a failure of scaling methodology, not a failure of neuroscience. Direct translation between the scanner and the syllabus is an architectural impossibility. True educational neuroscience requires stepping away from direct brain imaging and utilizing psychophysiological proxies instead. To salvage the promise of this field, we must stop looking directly at the brain and start measuring its secondary effects. This logarithmic scale visualizes Anderson's 7 orders of magnitude problem. The left represents neuroscience, measuring milliseconds and micrometers to establish cause and effect. The right represents education, a macro process over thousands of days. Between them lies an unbridged void of 5 full orders. Scientific inferences lose their integrity when stretched across this much missing data. The precise variables that dictate learning at the millisecond level are entirely washed out by the operational noise of the macro level. Any educational framework that claims to be brain-based, while ignoring these 7 orders of magnitude, is mathematically invalid. The most successful translation studies coming from leading educational researchers completely abandon the use of fMRI. Direct brain imaging is the wrong tool for designing instruction. It is functionally useless outside of a sterile laboratory setting. The methodological question then becomes, how do we extract reliable data on cognitive processes without an MRI scanner? We return to the logarithmic scale. A new block labeled digital learning environments drops into the empty middle gap. These environments provide the necessary middle ground. They allow for controlled data capture similar to a laboratory, while maintaining the real-world ecological validity of a standard classroom. Inside these environments, we can rely on psychophysiological proxies, alternative physical measurements that give us high-fidelity data on neural activity, requiring no direct brain scanning. Educational technology serves as the physical bridge required to make this research mathematically possible. We can observe this applied methodology in the work of researchers Kruger and Doherty, who examine cognitive load. This interface illustrates multimodal assessments. Combining EEG and eye tracking builds a proxy tailored for educational video. When a complex diagram appears in the player, the scrolling EEG wave at the bottom spikes in synchronization, providing instructional designers with real-time feedback on cognitive load. A similar application of proxies appears in Pachman's research on complex problem-solving environments. By tracking specific gaze patterns across a screen, researchers detect the exact moment a learner's cognitive model breaks down, transitioning from understanding to confusion. Detecting the specific contextual trigger of confusion via a traditional MRI scan is impossible. By tracking the eyes, we are tracking the real-time operational limits of the brain without ever needing to look at a single neuron. Another highly granular marker is pupillometry, measuring the exact diameter of the pupil in response to cognitive demand. Researchers Wong, Moss, and Shun found that pupil diameter serves as a highly precise, real-time marker for determining when students are generating self-explanation strategies while reading complex text. Beyond physical proxies, the digital environment also captures purely behavioral markers. Researcher Marzouk demonstrates how learning analytics can track student motivation and self-regulation directly within a digital platform. System data like click rates, pause times, and exact navigation paths serve as the behavioral exhaust of the mind's working memory. Combining a physiological proxy like pupil dilation with ClickPath analytics creates a comprehensive psychological profile of the learner. These applied intermediate analytics provide the rigorous truths about learning that the original neuroscience hype promised but could not deliver. The assumption that a laboratory brain scan can dictate classroom curriculum is obsolete. It is being replaced by a rigorous, multi-step engineering pipeline. This flowchart models the correct architecture. We establish the baseline by mapping fundamental neural functions upward into tested cognitive theory, like working memory. Next is the critical translation layer, converting those broad cognitive theories into measurable psychophysiological proxies. Those proxies are then tracked and funneled into actionable digital system metrics. Finally, those analytics inform system design to drive macro, long-term educational outcomes. This multi-layered framework provides the only scientifically valid method for spanning the 7 orders of magnitude. For educators and instructional designers, this dictates a clear shift in daily practice. Stop searching for generic, brain-based curriculum hacks. Do not attempt to design courses around the localized anatomy of the brain. Focus your attention strictly on interface-level variables. Optimize cognitive load, build confusion detection into your user interfaces, and monitor self-regulation analytics. The brain, the mind, and educational technology are deeply intertwined, requiring a holistic view that stretches from the isolated neuron to the broader neighborhood. Success in educational neuroscience depends on executing the specific engineering challenge required to bridge the gap between the laboratory and the learner.